Okay, so now we know what it means for two matrices to be similar. A matrix A is similar to a matrix B if A equals x times B times x inverse for some x. So what does it mean for a matrix to be diagonalizable? Well, by definition, we say that a matrix A is diagonalizable if A is similar to a diagonal matrix. So here's an example illustrating the equation telling us that a certain matrix is diagonalizable. Here I have a 4x4 matrix on the left. Let's call that matrix A. And what we're doing is we're expressing A as the product of three matrices. This matrix in the middle is some matrix D. And D is being multiplied on the left by a matrix X and on the right by a matrix X inverse. Notice that D here is a diagonal matrix. The only non-zero entries in D are off of the diagonal. So this equation is telling us that A is diagonalizable, and this is because A is similar to a diagonal matrix. Now remember, when a matrix is similar to another matrix, those two matrices share a lot of properties. And in particular, they have eigenvalues in common. Well, what are the eigenvalues of a diagonal matrix? The eigenvalues are exactly the diagonal entries. So that's one thing we can immediately infer here. The diagonal entries of D in the diagonalizable, or in this diagonalization, are the eigenvalues of A. So we see here, this one equation, among many things as we'll see in a moment, is telling me that the eigenvalues of A are -5, -1, 3, and 7. Great. So let's look at an example illustrating the power of this concept. So here I have a diagonalization. I have this matrix A, which is similar to this matrix D via this matrix X. So A is X times D times X inverse, and D here is a diagonal matrix. Well, one thing we said about similar matrices is that if A is similar to D here, the powers of A are related to the powers of D. And so one thing we could do is, if we wanted, we could calculate the nth power of A quite easily here. The nth power of A, which is A to the n right here, is equal to x times D to the n times X inverse. And the idea here is that D to the n is easy to calculate the nth power of because D is a diagonal matrix. So all we have to do is find the nth power of each of the diagonal entries. And that would be -1 to the n and 2 to the n here. We could then multiply x times D to the n times X inverse to get our formula for A to the n here. So rather than multiply A together a bunch of times, all we have to do is plug in the right value of n here, and we get a quicker result. So that's one useful thing we can do with a diagonalization like we have here. Now, it's important to point out that not all matrices are diagonalizable. Here, let's look at this matrix on the left here. This is an upper triangular matrix A, where the diagonal entries are 0, and in the top right corner we have the number 1. I'm now going to argue to you that this matrix is not diagonalizable. Well, what would happen if it were diagonalizable? Well, that would mean that A is equal to x times a diagonal matrix times X inverse. And remember, in the diagonal matrix, the diagonal entries are the eigenvalues of the matrix. But here A is upper triangular, and for an upper triangular matrix, the eigenvalues are the diagonal entries. So that would mean that in my diagonal matrix here, I would have to have zeros. But this is a problem because now my middle matrix here is the 0 matrix, and it doesn't matter what x is. X times the 0 matrix times X inverse is the 0 matrix. And this is impossible because my original A was not the 0 matrix. So this can't happen. A here is not diagonalizable because of this argument. So A is not similar to any diagonal matrix for this particular A. So what we have now is this new concept. A matrix is diagonalizable if it is similar to a diagonal matrix. we've seen an example, or we've seen a few examples now, of a matrix that is diagonalizable, but this is an example of a matrix that is not diagonalizable. So we'll want to have a theory which can sort this out. In other words, a theory which tells us which matrices are diagonalizable and which aren't. Here is another example. So here we have a 3 by 3 matrix that's diagonalized for us. A is x times d times x inverse. I want to take a look at the eigenspaces of D here. Well, D is diagonal, so when we go to look at the eigenspaces, all we're going to end up with as the bases are the columns of the identity matrix. For lambda equals -7 here, which is our first eigenvalue, we'll get that the eigenspace is spanned by 1, 0, 0 and 0, 1, 0. And for lambda equals 4, which is our third diagonal entry of D here, we find that for the matrix D, the eigenspace is spanned by 0, 0, 1. Well, what about the eigenspaces of A now? Well, remember, to get the eigenspaces of A, we take the basis vectors for the eigenspaces of D here and multiply by the matrix X. And what happens when I multiply X by 1, 0, 0 and 0, 1, 0? I just end up plucking out the first two columns of X. What about, and the thing to note here is that for lambda equals -7, the eigen vectors of A corresponding to -7 are exactly the first two columns of X here, and that's because the first two entries on the diagonal of D are -7. What about the second eigenvalue, lambda equals 4? Well, the eigenspace of D was spanned by 0, 0, 1. To get the eigenspace of A, we multiply 0, 0, 1 by X. Well, that will give us the third column of X, 1, -3, 3. And that's because this eigenvalue 4 is in the third position on the diagonal of D here. So what it's looking like from this example is that to get the eigenspaces of A, given this diagonalization, all we're really doing is we're looking at the columns of the matrix X that pop out of this equation.